Why does Roman concrete last 2,000 years while modern concrete sometimes fails in just decades? Walk along the coast of Italy. Look at the ancient Roman harbors. Massive stone piers, breakwaters battered by waves, salt water crashing against them for centuries. And yet, they are still standing. Now, look at many modern concrete structures. Bridges cracking, seawalls deteriorating, reinforced beams corroding. Repairs needed after only 40 or 50 years. How is that possible? How could builders from the Roman Empire create something more durable than what we pour today with advanced chemistry and industrial technology? The answer begins with a simple but powerful difference. Romans did not build the way we build. They built for eternity. Modern concrete is optimized for speed, for cost efficiency, for mass production. Roman concrete was optimized for endurance, and the secret lies in its ingredients. Modern concrete is typically made from Portland cement, a mixture of limestone and clay heated to extremely high temperatures. It hardens quickly, it's strong in compression, it's reliable, but it has weaknesses, especially in marine environments. Steel reinforcement inside modern concrete corrodes when exposed to salt water. Once steel rusts, it expands, the concrete cracks, water seeps in, the cycle accelerates. But Roman concrete did not rely on steel reinforcement, it relied on chemistry, specifically volcanic ash. The Romans used a material called pozzolana, named after Pozzuoli near Mount Vesuvius. This volcanic ash was mixed with lime and seawater, and something remarkable happened. A chemical reaction began. Over time, that mixture formed crystalline structures. One of the key minerals identified by modern scientists is called tobermorite. Another is philipsite. These minerals actually grow within cracks. Let that sink in. When tiny fractures form in Roman marine concrete, seawater seeps inside. Instead of causing damage, it triggers further mineral growth. The concrete strengthens itself. In other words, it heals. Modern studies published by researchers analyzing ancient harbor samples have shown that Roman marine concrete becomes more resilient over time, not weaker, stronger. Now think about that. A building material designed nearly 2,000 years ago improves with age. Modern concrete often does the opposite. Why? Because we chose speed over longevity. Portland cement revolutionized construction in the 19th century. It allowed rapid urban expansion, skyscrapers, highways, bridges, dams. It was predictable, scalable, industrial. But it also locked us into a formula optimized for fast curing and standardized production. Roman concrete cured slowly, sometimes very slowly. Their structures were not rushed. They did not have deadlines tied to quarterly earnings. They did not build for 30-year maintenance cycles. They built aqueducts meant to carry water for generations. They built harbors meant to resist waves for centuries. And they succeeded. The Pantheon in Rome still has the world's largest unreinforced concrete dome, nearly 2,000 years old, still intact. No steel skeleton hidden inside, just carefully layered Roman concrete. The lower portions of the dome use heavier aggregates. Higher layers use lighter materials like pumice. Weight distribution was intentional, engineered, calculated. So Roman concrete was not primitive, it was specialized, highly adapted to its environment. But here's the twist. For centuries, the exact formula was forgotten. After the fall of the Roman Empire, much of that large-scale infrastructure knowledge faded. Medieval builders did not consistently replicate Roman marine concrete. Industrial cement replaced ancient lime pozzolana mixtures. And only in recent decades have scientists truly begun to understand what the Romans achieved. Core samples taken from ancient Roman harbors revealed unexpected crystalline formations. At first, researchers thought impurities were accidents. Then they realized they were intentional.
The lime clasts in Roman concrete were not mistakes. They were part of a hot mixing process. By mixing quicklime at high temperatures directly into the aggregate and ash, Romans created reactive pockets within the material. When cracks formed centuries later, water interacted with these lime clasts, triggering recrystallization, self-repair. That is not myth, that is measurable chemistry. Modern researchers are now studying how to replicate these properties, not to copy the Roman formula exactly, but to learn from it. Because infrastructure today faces a serious challenge: climate change, rising sea levels, saltwater intrusion, extreme weather. If we could engineer concrete that strengthens in marine environments rather than degrades, it would revolutionize coastal construction. And here is the deeper lesson. The Romans were not more technologically advanced than us in every category. They did not have computers. They did not have digital modeling software. They did not have modern material science labs. But they had time. They had observation. They had iterative experimentation across generations. Their empire spanned centuries. Techniques evolved, improved, refined. Knowledge accumulated. Today, we sometimes assume technological progress is linear, but history shows something different. Certain solutions appear, then disappear, then reappear centuries later under scientific rediscovery. Roman concrete is one of those solutions. It challenges a modern assumption that newer automatically means better. Sometimes newer means faster, cheaper, more scalable, but not necessarily more durable. And durability matters, because when bridges collapse, when seawalls fail, when buildings crumble prematurely, the cost is not just financial, it's human. So the question becomes, why didn't we continue using Roman-style concrete? The answer is complex. Raw materials differ. Volcanic ash like Pozzolana is geographically specific. Industrial expansion favored uniformity. Steel reinforcement enabled taller, thinner structures. Economic incentives rewarded speed. Roman construction was labor-intensive. Modern construction is machine-driven. And yet, scientists today are revisiting ancient formulas, testing volcanic ash mixtures, studying lime-clast reactions, modeling mineral growth in cracks. In laboratories, researchers have successfully recreated Roman-style self-healing concrete, which means the knowledge was not magic, it was chemistry. We simply stopped using it. There is something humbling about that. An ancient civilization, without modern technology, created a building material that still outperforms many of our structures in specific environments. Not because they were superhuman, not because of lost alien technology, but because they optimized differently. They built for centuries. We often build for decades. The ruins along the Mediterranean coast are not just relics, they are evidence. Evidence that innovation doesn't always move forward in a straight line. Sometimes the past holds answers the present forgot. And perhaps the most powerful takeaway is this: Roman concrete lasts 2,000 years, not because it was stronger in every way, but because it was smarter for its purpose. Designed for the environment, designed for time, designed to endure. And maybe the real failure isn't modern concrete. Maybe the failure is forgetting that durability was once the highest priority of all.